that we've already done, right? Just sort of, again, building and building on stuff from first semester. So not only are we going to be using stoichiometry, right? We're going to be using the concept of what a mole is. We have molar mass coming back in. We have this new thing called molarity, right, which we have to incorporate. We have some percent by weight concept here, which is slightly new. So we will go through a bunch of examples. It's going to be math heavy, so mentally prepare for math right now. Okay, so let me share my screen. Okay. So we are not going to go over dilution just because I realized that there's not going to be enough time to do that. So we are going to go over molarity. There is dilution in the lesson. I think it's a little easier math-wise for dilution. So you're going to have to go back into this Canvas lesson and take notes and understand dilution on your own. So our objectives today are going to be to define molarity, solve molarity problems using stoichiometry and given information from the word problem, and Module 5 DBA. So if you haven't taken notes on this yet, I encourage you to take notes, and I'm going to go slow on some of the stuff so that you have time to write it down. So right now I'm actually going to give you an entire minute to write the definition of molarity. I would write all this bolded stuff as well, right, because this is kind of the shortcut. Make sure you know what the unit is. It's a capital M, has to be capital. Okay, so I'm going to start talking. If you're still writing, that's fine. So molarity is a unit of concentration expressed in moles of solute per liters of solution, right? So the shortened way to think about it is that it's moles per liter. It is a capital M, right? Lowercase m is usually used for mass. So if you use a lowercase m, it's not the biggest deal in the world, but the official chemistry way is giant capital N. So of course the moles are going to be from our solute, which is what's getting dissolved in a substance. So for example, let's think about sugar getting dissolved in water. For our molarity of our sugar water solution here, we're going to have the moles of sugar, right? Because sugar would be our solute divided by the moles of the solution in liters, which would be water. And of course, liters is a new use here, right? Okay. So how do we find moles again? So this is a review from first semester, and shouldn't be too complicated, but we're going to first of all find moles from grams, and then we're actually going to find the molarity of this salt water here. So 110 grams of NaCl are dissolved into 5,000 milliliters of water. What is the molarity? Okay, making sure I didn't write any other words there. So first we need to find the moles of our solute. Keeping in mind our solute is what's getting dissolved in the solvent, right? Which is really annoying because they all sound similar. Solute, solvent, solution, right? So our solute is our solid, which is going to be our NaCl. So we need to know how many moles of NaCl we have. So we're going to start with what we know. We know how many grams we have. We have 110 grams. We get our molar mass of NaCl from the periodic table, right? So all I did was go to the periodic table, look at the mass for sodium, and add it to the mass of chlorine to get 58.4 grams. That will equate to 1 mole of NaCl, right? This should be a review. Again, we're setting this up so that we can cancel units. So we are starting with grams, we don't want grams. We're putting grams on the bottom here so that we can cross grams out, which I will do here, right? So grams will cancel, and we're left with just moles of NaCl. So that's great. That's the first step that we needed, was our moles of our solute. So we know that if we do this math, 110 divided by 58.4, we get 1.88 moles of NaCl. Not so bad so far. Part 2, we are going to need to figure out how many liters we have. Right? Our solvent is water. We have 5,000 milliliters of water. That just comes from the question. So we need to convert milliliters to liters, right? If you know the decimal moving shortcut, that's great. If you don't, you can use a stoichiometry setup here to figure this out. We're starting with 5,000 milliliters of water. We know that 1 liter has 1,000 milliliters, right? Why is milliliters on the bottom? Because again, we want to be able to cross out that unit so that we're left with the unit that we want. If we perform this math here and do 5,000 divided by 1,000, we get 5 liters of H2O. So now, based on that, what do you guys think we're going to do? We now know our moles of our solvent, our moles of our solute, and our liters of our solvent. So what are we going to do next? Based on what molarity is. Look back at your definition of molarity. Well, if anything, let's start with what is the definition of molarity, okay? Thank you, Abby here. We're going to divide the moles of our solute by liters of solution. Great. So now it becomes a simple division situation. Molarity is moles divided by liters. We have 1.88 moles NaCl divided by 5 liters of water. If we do that calculation, 1.88 divided by 5, we get 0.376 giant M, or molar. Right? So if you ever want to say that unit out loud, it's molar. M-O-L-A-R, sounds like the teeth. Right? It's describing molarity. So the molarity of our solution would be 0.376. Okay, that was the basic, easiest kind of question that you'll see, where you're given grams of something and you have to find moles, right? You maybe have to convert to liters from milliliters, or usually you won't see any other types of liters, but you might see like kiloliters, just so that they can make it harder. You'll usually see milliliters or liters, thankfully. Okay, so we're going to try a harder one now. So I'm going to give you guys an opportunity here to write this down, because I think having examples written is super important, right? Because if you get stuck, you should go back to that example and look at what we did in the example. So I want you to actually write the question, write the equation, and then we'll talk about the rest, right? And you can kind of write as we go. So I'll give you guys a little bit of time here to actually write down this question. All right, so give me a 1 in the chat if you have this written down. You're ready to start figuring out what to do here. Okay, Abby's ready. I'll assume that means other people are ready, but if you don't participate in the chat, I'm not going to know what you're thinking. So, just to read the question here. How many milliliters of a 2.5 molar hydrochloric acid solution would be needed to react completely with 32 grams of magnesium metal? Okay. We're looking for an answer in milliliters of hydrochloric acid, right? And they tell us the molar concentration here, or the molarity of that hydrochloric acid. We're given the amount of magnesium, right? We're reacting completely, meaning we're using all of it, the 32 grams of magnesium. So 2.5 molar solution, right, can be rewritten as 2.5 moles of HCl to 1 liter of HCl. That just comes from the definition of what molarity is, right? It's moles per liter. So we can separate that unit, and notice we keep it HCl on both the top and the bottom of that fraction, right? So it doesn't become, for example, like moles of hydrogen per liter of chloride or something like that. It becomes moles of HCl per liter of HCl. Again, we're going to start with the magnesium, right? Because we know that we have 32 grams of it, and they tell us that we're looking for milliliters of hydrochloric acid, right? So we're not going to start with hydrochloric acid if we're looking for that. So again, we set this up in our stoichiometry. I'm going to call it a railroad track because that's essentially what it looks like. We start with what we know, 32 grams of magnesium. Again, we want to convert this to moles. Why? Because we pretty much only know other things about moles. We don't know anything about grams here. So we're going to find the molar mass of magnesium from the periodic table. It's 24.31 grams per 1 mole of magnesium. That's going to allow us to cross out our grams, and now we're in moles. Now we're going to use a concept that we used when we did limiting reactant, right, which is that the equation tells us the ratio of moles to moles. So for every 1 mole of magnesium, right, because it doesn't have anything in front of it, we need 2 moles of hydrochloric acid. So knowing that information, right, using just the coefficients here from the equation, we can convert into hydrochloric acid, right, from magnesium, which is what we want to do, right? We're trying to find out how many milliliters of hydrochloric acid we need. So we're going to put 1 mole of magnesium on the bottom so that we can cancel that unit. And now we are left with 2 moles of HCl, which is great. But again, that's not what we want. We want to know how many milliliters. So we need to get from moles to liters. Well, guess what? We know the molarity, which is moles per liter. And remember, you could switch those two around because they equal 1, essentially, right? 1 liter per 2.5 moles is the same thing as 2.5 moles per 1 liter. They're equivalent. So in this case, we're going to put 2.5 moles of HCl on the bottom, right? Because we want to get into liters, and we have it on the top here. Now we can get rid of moles, and we're in liters, which is great. However, we want to be in milliliters. So again, we're going to do our conversion to milliliters. If you don't know this one, I would definitely write that down, right? Because it's going to be frequent in these kinds of problems. But there are 1,000 milliliters in 1 liter. So we've left liters, and we are now in our final unit here that we want, milliliters of HCl, which is what we're looking for, right? So now we actually just do the math. So take your calculator, get mine out, and see if you get the same answer. And type in the chat what you end up getting when you go through all of this dimensional analysis. And remember, you do 32. Whatever's on the bottom, you're going to divide. Whatever's on the top, you're going to multiply. And actually, while we're waiting on people to get an answer here, I'm going to edit this slide because I just realized now the magnesium actually isn't even dissolving into the HCl necessarily, right? So that's not 100% true, what I wrote there. But it is important to keep them in mind that magnesium was what we're starting with. HCl is what we're looking for. Okay, anybody get an answer from this one? Awesome, thank you, Abby. I think it's just me and you right now in this virtual session. You're right, that's exactly what I got, 1,053.06. Right, so that is, again, make sure you include your unit, milliliters of HCl, right, would be your final total answer. So then, let's do another example. And it's going to keep getting harder here, right? So this one adds in a new concept of percent by weight, which sounds complex, and I kind of do it a little bit differently than Canvas does it in the lesson, right? Both ways are totally fine. You'll still get the same answer, but the way that I do it makes more sense to me, right? If this isn't making sense to you, this multiplying by 0.65, which I'll explain in a second, you can always see another way to do it in Canvas. So this time our question says, how many grams of iron metal do you expect to be produced when 215 grams of a 65% by mass iron 2 nitrate solution reacts with excess aluminum metal? So again, what things are we actually looking at here? We're looking at our aluminum, which is excess, and we're looking at our solution here, which is iron 2 nitrate solution. If you're ever confused about what the solution is, look at the solid gas liquid little, I guess, suffix here, right? AQ means aqueous, which means it's dissolved, which means it's a solution. So I'm going to give you guys time to write this down again. just because I feel like, again, I want you to have these examples written, right? Because it's going to help you later when you get stuck. So I'll give you guys like 1 minute to write-ish. And when you're done writing the question down, if you finish and no one else says anything, keep writing, I guess, the example. But just type a 1 in the chat so I know that you're done writing. Okay, thank you, Abby, for letting me know. Okay, so a 65% by mass solution technically means that for every 65 grams of iron 2 nitrate that you have 100 grams of the solution, right? So in theory, you could think about it if like you were looking at a liquid and it's 65% sugar or something like that, right? So this is basically telling you how much of the iron 2 nitrate can actually dissolve in 100 grams. Also, it's telling you that it's not 215 grams because it's only 65% of it. So the easiest way for me, right, because the percents make sense to me pretty easily, is we can just take our starting value of the iron 2 nitrate, which they tell us is 215 grams, and we can multiply it by 0.65 to find out what 65% of that is. Because again, that means that 139.75 grams is the amount that's actually dissolved in the solution. Okay. So knowing that, right, you can always just take that percentage and multiply it by whatever grams they give you. Or like I said, you can check Canvas for an alternate way. They actually include it in the stoichiometry, but I find it confusing the way they included it, so I chose to do it my own way. We're going to start with that value that we have here, right? Because we have excess aluminum, which means we have endless aluminum. We don't care about that. But we want to know how much of this iron metal we get. So we're actually looking for a product here, right? We're looking for straight up solid iron. And aluminum is in excess, so we pretty much ignore. What we really care about is this aqueous solution and how much of that iron is going to become a solid. So we start with the 65% by mass iron 2 nitrate, which is 139.75 grams. And let me tell you, writing out FeNO3 a million times was so frustrating yesterday. I was like, ugh. Okay, so we have that in the solution, right? Again, what are we going to do to go to moles or in grams? We're going to use the molar mass. So if you add up 1 iron, 2 nitrates, 6 oxygens, you get 179.3 grams. Right now, the nice thing, guys, I'll tell you a little shortcut. You can actually Google molar mass FeNO3 and it's listed there, right? So on some of these bigger ones where it's like gonna take you 5 minutes to figure out the molar mass, you can always Google that, but make sure you understand how to get that molar mass, right? Because that can be a question that you'll see. How did you get that molar mass? And if you're like, I Googled it, no, you would have had to add iron plus 2 nitrates plus 6 oxygens to find that molar mass. Okay, regardless, back into the math. So now we have taken grams and gotten rid of grams, and we're in moles. Now, same thing with limiting reactant. We're looking for this solid iron, Well, we see that conveniently they have the same ratio here. 3 is the coefficient for our iron 2 nitrate, and 3 is the coefficient for our iron. So we know that for every 3 moles of iron 2 nitrate, we get 3 moles of iron. Now again, okay, we seem like, all right, we're making progress. We're into iron already. We're in moles of iron. Is that what we want? Well, let's check the question. We want to know how many grams of iron metal. So we go to the periodic table to find our molar mass of iron, which is 55.85. That will allow us to convert between moles and grams. So now we end up with grams as our final unit of iron. That's exactly what we want. So now we actually just have to do the multiplication. So we're going to take 139.75 divide by 179.3. Here we would really be multiplying by 3 and then dividing by 3. That essentially becomes 1, so I'm just going to ignore that. And we're going to multiply by 55.85. And you should get 43.53 grams of iron as your final answer. So the trick on this one was that we weren't given molarity. We were given this percent mass solution, which is a new kind of way to see that. Again, that means that only 65% of that solid mass actually dissolves and becomes part of the solution. Okay. How are we feeling about this so far? Let's see if we can kind of summarize the steps. I have a feeling Abby's going to be the only one to talk to me. But step 1, right, is to write what you know from the equation, right? We know we're looking for grams of metal. We know 65% mass solution of the iron 2 nitrate, and we know that aluminum is in excess. Step 2 is going to be figure out percent by mass or molarity. So in the first or the second example we did, right, we actually saw that the molarity was given to us, so we could break that up into moles over liters. In this situation, we're given a percent by mass, so we can figure out what percent by mass actually goes into that solution. Then 3 is to do the stoichiometry, which again, depending on what you know and what you're looking for, right, it'll tell you what to start with. If you have an excess of something, that means that you don't need to use it, right? It's available as much as you could possibly want. You're basically going to be going between moles and grams, right? Possibly liters. And you will have coefficients from the equation, right? Which is why you're given the equation. So it's not too many steps here, but it can be easy to get confused, right? Now, here's the thing. You might have actually set this up wrong. And you'll figure it out as you try to go through and cancel units. If your units aren't canceling, that means you need to go back and revise, right? That's why I actually physically cross out the units. Are they canceling? Am I doing this correctly? Okay, so now we're going to try this one independently, and then we're going to go over it. So, how many grams of chlorine gas are needed to react with 3.5 liters of a 1.7 molar potassium bromide solution? Pretty complex. So start by writing what you know, right? And we'll go through this one semi together, but I want you to also try on your own. So right now, just list out what you know from this question. Okay, so here's what I wrote as what I know. We're looking for grams of chlorine. We know that we're starting with 3.5 liters of potassium bromide. We also know from the molarity that we have 1.7 moles of potassium bromide to 1.7 liters of potassium bromide. So you want to write those two things as separate ideas here, right? Because they're telling us the amount of liters we have, but we also know the molarity, and those are two separate ideas, essentially, especially when we're setting up our stoichiometry equation. So now we'll try to set up the stoichiometry. I didn't make a box, I realize. Okay. Oops. I think that should be enough boxes. We'll find out. So what do you guys think we will start with? Looking at what we know. We can't start with chlorine because we don't know that. Are we going to start with liters or are we going to start with molarity? Okay, good guess, Abby. So that is, you could try to start with molarity. Now, you're going to run into an issue because liters is really where you want to start because it's by itself. Anytime you have a fraction, right, that's usually going to be later on in the equation. Now, you could have tried to start with molarity, you would have got stuck, right? So then you would have known, okay, go back and try liters. I happen to recognize that because I've done 7 million of these, right? So kind of once that happens, you'll see the pattern. So we're actually going to start with the 3.5 liters of potassium bromide. Why? Because then we can use this molarity. We can say 1.7 liters is equal to 1.7 moles. Now we have gotten rid of liters, right? And let me fix my units so that they're the same. And we're in moles, which is going to be helpful to us, right? Because we can use the equation to tell us coefficients of that relationship between chlorine and potassium bromide in moles. So now we go back into the equation. And we see that for every 2 moles of potassium bromide, we only have 1 mole of chlorine gas. So that would tell me, first of all, think about what's crossed out already. Liters are gone. We need moles of KBr on the bottom. So 2 moles KBr is equal to 1 mole chlorine. Okay, liters are gone, moles of KBr are gone. We're now just looking at moles of chlorine. That's good that we're in chlorine, right? Because we're looking for something about chlorine, but we're looking for grams. So not moles, but grams. So now this is when you would go to the periodic table to find that molar mass of chlorine. And remember, chlorine gas is 2 chlorine molecules put together, which means that we're going to take, if that could be any smaller, can't see because of the chat. There we go. So chlorine's molar mass is 33.45. We're going to times that by 2 because chlorine gas is 2 molecules of chlorine put together. So we know then that our molar mass of chlorine gas is 66.9 grams per 1 mole of Cl2. So once we multiply all this stuff together, will we get the right things? Well, let's make sure our units cancel. We started with liters. Liters got canceled here. We're in moles of KBr. Moles of KBr got canceled. Chlorine, moles gets canceled. And we're left with grams of chlorine, right, which is exactly what we want. We're looking for grams of chlorine. So now we would actually multiply all of that out, right? Doesn't help that I colored all over it, but we would do 3.5, 1.7 over 1.7, that's 1, right? So we can kind of ignore that. You could also multiply by 1.7 and divide by 1.7. Then we're going to divide by 2, and then we're going to multiply by 66.9, and you should get 117.08 grams of chlorine gas. Okay. So I don't think we're going to have time to do one more example and do the DBA. So I will tell you that this other practice question comes from Canvas, right? And there's an option for you to put your answer in and see if you get it right. So I encourage you to try this and go to the lesson in Canvas and keep trying, right? Again, the only way to get better at these problems is to try, right? And like I said, you're going to see patterns. You're going to say, oh, I know what that means. Oh, I see what to start with, right? This second example has that 85% by mass. But it's 251 grams, 85% by mass, right? So using that information that we used in our third example here, how do you find a mass, percent by mass? Okay, so I encourage you to try this question in Canvas and submit it. They had a few other examples as well. So for our DBA, we're all going to go to this Google Doc if you would like to do the DBA right now. And there are 3 questions. So you're just going to put your name, and then you're going to put a response to these 3 questions. The first question is going to be, what is the difference between a solution and a mixture? That's something that we discussed in the last virtual session. Question 2 is going to be, what is molarity? Which is something we defined in the beginning, which is why I emphasized writing it down. And then our third question is going to be, what do we need to calculate molarity? Which can essentially come from the definition. So when you think you have an answer, right, you're just going to go ahead and type it in the box underneath the question. You can use your notes, right? You can look back at lessons. That's why we're going to spend some time here. So take the time to, really think about the answer. And then, of course, I will be providing feedback for you or answering questions for you if you get stuck. Great start on your answer, Abby. A mixture combines 2 or more substances, and they keep their individual properties. Excellent. And I am going to keep this document open probably until Monday, right? So if you don't get a chance to answer all the questions right now, you can continue answering them through the weekend. And I will leave you a comment if I see something that I think you should revise. Excellent answer, Abby. Perfect. Molarity is the number of moles of solute divided by liters of solution. Okay, and other people who are here, right, who aren't typing in the document, haven't been typing in the chat, you're not participating, right? So in fact, I'm only going to award the code word to Abby here because she's the only person who's participated. Just sitting in the lesson is not enough. You need to be engaging in some way, right? This first question is something we went over last week. Everyone should be able to answer that. So Abby, I'm going to send you an email with the code word in it. And that code word is going to allow you to get 5 bonus points on this quiz, right? Because it is a challenging quiz. If you get 100 on the quiz, you could use those bonus points on something else, okay? Otherwise, guys, next time in the virtual session, you got to show me that you're alive, that you're participating. Even if you're just typing a 1 to tell me that you were done taking notes. Abby was the only person who did that. Morgan wrote her name, right, but nothing else. So I have no idea if you actually absorbed any of what happened here. So Abby, you will be getting 100% on the DBA. I will email you with that code word, right? Otherwise, guys, keep practicing these molarity problems. Use them to help you.